Alright, explain the meaning of the slope of a best fit trend line and identify whether the slope itself is a variable. Alright, so in physics, slopes have meanings. They tell a story about the real world. Or, a better way to say that, sorry if you just erased, they tell a story about the physical world. Physical world. This is physics after all. Often it is easier to see the meaning than to describe it with the appropriate and precise language. So in physics, sometimes just saying what you see is the hardest part. So how do you use precise language to explain this? What is this? This is a slope, and that slope has meaning. What is the meaning? Okay, so we have the days elapsing, and we have the plant growing in height. So what does this slope mean? So if we calculate the slope, rise over run, let's just do this really quick. So 2 over 1, 2 over 1, that equals 2. So what this means is that each day, or each one day, the plant grows 2 centimeters of height. And so that's how you would explain what the slope means, or the value of the slope means. And it seems easy enough, but it can get a little bit tricky, and there's a little bit of a language scaffold that I like to use just so that we are precise when we are describing the meaning of the slope. Okay, let's see this graph. It's a little blurry. We have study time over here on the bottom. As study time is increasing, your score is increasing. This is very true. If you study for longer, you're going to get a better score. And the slope is 20 over 1. So for every 1 hour, so let's think about so the units of the slope is 20, I think it's points, divided by 1 hour. Rise over run. I'm just including the units in my slope, and that always helps me describe the meaning of the slope. So for every 1 hour of study time, 1 hour, I'm going to use HR to shorten hour, the scores increase by 20 points. The scores increase by 20 points. And that's a great explanation of the meaning of the slope of that particular graph. Okay, so we got this guy stretching back a slingshot, and he has a certain distance that he's pulling it back, and anytime he pulls it back, it's going to require a different amount of force. So we have distance and force. Force is measured in newtons. We'll learn about that. Often we use x for horizontal distance in physics. If we're pulling something back horizontally, you're going to use x to represent the variable distance. And we'd use y if it was a vertical distance. It makes sense, right? Okay. So let's see. What's the slope of this line? We have a lattice point here, a lattice point here. 40 divided by 0.4, is that 100? Let me just do that really quick. 40 divided by 0.4 is 100. Okay, I knew it. I just wanted to make sure that I was right on these videos. Okay, so 40 divided by 0.4, 40 divided by 0.4 equals 100, and I want to include my units, and these are newtons per meter. 100 newtons per meter. Okay, so we want to fill this in. So for every 1 meter of pullback distance, I don't know, we can just say pullback distance. Pullback distance. Boom. The force increases by 100 newtons. By 100 newtons. Okay, so if you're noticing a little pattern here, we have this for every blank of blank, there is an increase or decrease by a certain amount of whatever the rise is. So we're going to talk about that. For every blank of blank, the scores increase or decrease by, I don't know, whatever the rise is of your slope. Last one. Okay, so this one we got speed and we've got pulse. So your pulse, beats per minute, that's how often your heart is beating. Ba-boom, ba-boom, ba-boom. And your speed, this looks like it's in kilometers per hour. So maybe we have a fast runner, and as they run faster, their pulse increases because they're using more oxygen, their body's working harder, and so if you run really fast, you'll notice that your pulse increases. Well, that's what this scientist decided to graph. And let's see what's the slope of this graph. We have, I'll just kind of see here, we got maybe like 10 is our run. I don't like to write that there. Let's do it like right there. 10 is our run, and our rise is about 20. Or no, 40. So 60 to 100 is about 40. You know, this isn't 10. That looks like about 8. So if I'm thinking about the beginning to there, coming down, that's probably about 8. So 40 divided by 8. Just thinking about the slope on the fly. I'm not really being too precise right now. That's because I don't want to take too much of your time with this video. 40 divided by 8 is 5. So our slope is 5 BPM divided by kph. So how do we say this? For every 1, why do I keep saying 1 here? Why do I keep saying 1? That's because 5 is the same as 5 over 1. This fraction here, it's the same here. Let me draw this a little bit differently. Let me just go. This is my rise, and this is my run. Okay, it's the same thing. So for every 1 kilometer per hour of speed, there is an increase in heart rate of 5 beats per minute, or a pulse of 5 beats per minute. So for every 1 kilometer per hour of speed, the pulse increases by 5 beats per minute. So if you've divided out, like you could have said for every 8 kilometers per hour of speed, there's an increase in 40 beats per minute of pulse. But because we divided 40 divided by 8, and that equals 5, and that then we're going to be using 5 over 1. That's our new fraction. And it's always better in physics to do that, just to use your calculator and divide. Even if it's a decimal, that's fine with me. Okay, so you just want to practice the sentence structure for every value and units of the run. Value and units of the run. Value means number. So how big is your run? In this case, our run is 1. It's 1 kilometer per hour. So that's my value, and that's my units. Okay? For this, and so yeah, that's how you want to do it. Of your independent variable. So that, because we're talking about the run, you're going to just write in your independent variable right there. So for example, in this one, for every 1 value kilometers per hour, which is my unit of speed, I just wrote the independent variable there. Remember, that's my whatever the variable is written on the x-axis. So write in your independent variable there. The dependent variable, so just look at whatever the dependent variable is, pulse. The pulse will increase or decrease. In this case, it's increasing. by the value in units of the rise. So what is the value in units of the rise? The value is 5 and the units are beats per minute. Okay? So that's how you can fill in that explaining the meaning of the slope, and then you have the right structure every time and you're including all the right things. So that's your sentence structure. It's going to come easier. This is probably the most complicated way to think about it. It'll just be really natural when you start just looking at your slopes and start writing it for every blank. You know, just start sentence starter with for every, and you'll get there in the end. I believe in you. Okay. Now this is cool. This is what I think where physics starts to get more interesting, is that slopes are also variables. Sometimes graphing two relationships reveal a new variable. This is going to be really a powerful tool for you guys. So sometimes if I were to ask you, what's the meaning of the slope? And you'd say, okay, well, the slope is 5, and so for every kilometer per hour of speed, the pulse increases by 5 beats per minute. I'm like, cool, you've explained the meaning of the slope of that graph. I love it. In other cases, well, you gotta look a little bit deeper. There could be some magic here. Okay, so let's look at this mass on the y-axis and volume on the x-axis graph. So the rise in this case, what's the rise? What variable is the rise? It's mass, measured in grams. The run is the volume, measured in cubic centimeters. Therefore, the rise divided by the run is mass over volume, which is, now you got to think, what is mass divided by volume? Have I ever seen that before? And I know that you guys have because you've studied it in the past, but you might have forgot. Mass divided by volume is density. Mass divided by volume is the density. So remember, density, it's how much mass you have in a given amount of space. So here's a cube here. It's a certain amount of cubic centimeters, and this one on the left is more dense than this one on the right. If we were graphing this in class, we would probably go over the formula for density, which is this is actually the Greek letter rho. You don't have to remember that right now. But density equals mass over volume. So if we did the rise over run and we find out that the slope of the graph is, well, it's saying down here that it's 8.89. Well, the substance represented in the graph has a density of 8.89 grams per cubic centimeter. It's got a density. Centimeter. Grams per cubic centimeter. And I just used the units of my slope. Grams is on the rise and cubic centimeter is on the run. So the deal here is, for example, like if I were to say the blue line is substance A, the purple line, and the green line is substance B, which of the two substances is more dense? And you'd go, hey, I know that this green line has a steeper slope, and because slope is density, then that means that this green line it has more density because the slope is bigger, and that's how you would start to answer some questions. And this graph the slope of this graph reveals a new variable, density. Let's do one more. So here we have another graph. We have distance on the y-axis and time on the x-axis. The rise is distance measured in hours. Nope. The rise is the distance measured in, there's a little typo, that's okay. Distance measured in miles. I bet you can figure out what the meaning of this slope is before I explain it. So see if you can think ahead of me. Measured in miles. What is the meaning of the slope of this graph? The run is the time measured in hours. Therefore, the rise divided by the run is distance over time, which is, so what is distance divided by time? It's speed. You guys know this. Distance divided by the time is speed. So we'll write that here. Speed equals d over t. The car is traveling at a speed of, so what are our units? The units of the rise are miles, and the units of the run are hours. And you know this because anytime you get in a car, you see this on the dashboard. Miles per hour, or MPH for short. So make sure that you, so yeah, I could ask you which car is moving faster, the green car or the red car, and you can tell me that, hey, the green car is going faster because it has a steeper slope, and the slope of this graph represents speed because the rise is distance and the run is time, and distance divided by time, rise divided by run, that equals speed, velocity. Okay, helpful hints. Use the definition of slope. Rise over run, people. Rise over run. So much answers can be solved just by thinking about rise over run, either the units or whatever. Look at the units of the slope and ask yourself, do these units look familiar? For example, in this case, if you see miles per hour, you're like, okay, I know that's a speed. Perfect. I know what the meaning of the slope is. As we study formulas in class, look for quotients. What is a quotient? Don't worry, this is a quotient. You've seen that before. This, the dividey thing. A quotient is anytime you have two things that are divided by one another. For example, here we have force over divided by mass, and force divided by mass equals acceleration. And so if I were to ask you, make me a graph that the slope is acceleration, that sounds like an impossible task. Make me a graph whose slope is acceleration. What, Mr. Rip? Well, it's not so hard if you think, okay, so the rise is force in newtons, and the run is mass in grams or kilograms. Then if you have a line across it, and you figure out, oh, what's the rise divided by run? Well, this rise divided by run is force divided by mass, so this slope, it is the, well, I shouldn't point my arrow there, I should point it to the rise divided by the run, is the A. And we haven't studied A is the symbol for acceleration, F is force, and M is mass, but we'll get there soon. But anyways, I want you guys to have a heads up that some slopes can have a meaning that is a new variable. Other slopes don't. Other slopes, a force divided by distance, force over distance, that's not really a thing in this physics in this context here. So there's no new variable. But sometimes there is a new variable, and you're going to have to be able to analyze slopes where the slopes represent something new.